So my name's John DiGilio. I work within the Network Platform Solutions Group at Intel. And today I'm going to provide an overview of both some of the technology alignment we've done with NGINX, as well as some of the future investigation that we're looking at. A lot of this work applies not only to Intel architecture, but will benefit other architectures too. So you'll see some of our work in the open source community, as well as some future investigation, again, around open source. Because we have performance numbers here, Intel guidance requires us just to go ahead and give you that lengthy disclaimer to look at. All right, so I think I was looking at the schedule, and this is probably the 5th or 6th session that has one of the focus areas around the increased security processing needs. And it's not just security. I mean, generally, if you look at the increased number of mobile devices, I think there was a session on mobile devices and the crossover from fixed to mobile. But we're just doing a lot more, and we're demanding a lot more of the compute nodes. And so that's where some of our R&D effort goes into how do we get the most out of an IA-based server. Today's discussion is going to touch on a couple areas. One, around when you need additional security processing, but then also just generally handling the number of connections per second that you're being asked to process. And so I think we all know about the transport layer security. We have some performance numbers here for a TLS 1.2 handshake we'll talk about. But generally, depending on the NGINX deployment model, you may be doing more security, you may be doing just more session setup and teardown. And so we're here to work with NGINX to make sure you get the most out of our best-in-class processors. All right, one of those technologies that we've added in addition to our ever-growing list of CPUs is Intel QuickAssist technology. Now, as you've heard from other speakers, we had Nick from Cloudflare point out the fact that our latest generation Xeon processors include very good processing for AES GCM, and so at least for the symmetric portion, once you have the session set up, you're getting very good performance from our processors. But these are compute-intensive algorithms, especially when you look at some of the other algorithms, and especially when you're setting up the public key exchange. So the setting up of a session requires a public key generation and exchange, and that's a compute-intensive algorithm. So we acknowledge that, and we have additional hardware that augments the CPU capability when you need that level of security processing. The other hardware-specific element that's in there is compression. Compression when you're looking at WAN optimization, or compression when you're looking at storage backend. Again, this is an area where you can look at hardware adding to the efficiency of CPU. By the way, I don't mind taking questions during the session. We should have a few minutes after the session, but go ahead and interrupt me if you want to get further clarification on some of these points. All right, so Intel QuickAssist technology from a form factor aspect, as I said, this is silicon-specific hardware, and it's available in current generation in a unique chipset we call the Intel communication chipset that goes along with our CPU roadmap. So that gets combined with our current generation Xeon processors. In addition, we've also taken that hardware technology and have integrated it into our multi-core Atom SoCs. So if you look at the Avoton family class, this will include versions that have that crypto acceleration built right in. And then another form factor that's readily available to add to existing servers is you could put that technology in a PCI Express add-on board. And we have several vendors that provide that those modules at different capacity, different PCI connectivity. Now, when we do this, that's the hardware aspect, that's the form factor. We also acknowledge that it has to be usable, and it has to be easily consumable. And so Intel will always look to enable, with the open source community, working with folks like NGINX closely to make sure that this technology is consumable. So we have drivers and patches available with the both OpenSSL and NGINX components that we'll talk about a little bit more. Before we get to the usability of this hardware, we also have to acknowledge that the difference between an async approach and a synchronous invocation. So when you're running on CPU instructions, clearly a synchronous invocation gives you the best efficiency. On the other hand, though, when you're using hardware acceleration, it's the async invocation that's going to be able to add the latency and get you the efficiency. And so there's a trade-off there in that clearly, as this graph shows here, when you add more and more worker threads, you're effectively accomplishing an async type of invocation approach from your application. But the most optimal use of hardware would be for the application to understand that there's hardware underneath and look at an async implementation. So we've been working closely with the OpenSSL Foundation to look at how do we update the OpenSSL API itself, as well as the engines underneath, to give you that flexibility to use the hardware efficiently. That's available, as you'll see. You could download that from our website. It's available in a developer tree at OpenSSL, but it's also being put in a mainstream release with the upcoming release of OpenSSL. This chart is just showing you the concept there of synchronous versus async and the need for async support when you're adding hardware to help with some of these compute-intensive algorithms. Again, this is not specific to Intel architecture. These concepts are relevant to all architecture and is really tied to the fact that you're using a hardware accelerator to augment the CPU capability. All right, so again, to put it in perspective from a software stack, and unlike a lot of the other sessions here where you're looking at it from an application perspective and above, so NGINX and higher, as a silicon vendor, we're looking at really getting the most out of the platform, so we're looking at lower layers. This is OpenSSL and below. And so we make sure that our drivers and then the patches to OpenSSL give you the most out of the hardware. And as I said, this requires both patches to OpenSSL as well as patches to NGINX when you're using an async mode. All right, so this is the slide that brings home the point that when you have a security-centric deployment of NGINX, so whether this is an SSL proxy or you have lots of HTTPS sessions that you're setting up and tearing down because you're in the middle, that public key exchange is a compute-intensive item, and it's one that ideally lends itself to benefit from hardware acceleration. As you can see here on this chart, as well as at our demo booth, you could complement the CPU, and with just one of those QuickAssist add-on modules, you're getting a 6 to 7x capability throughput. And so again, that's a trade-off that you're making between using a homogeneous server-type pool or whether you want to add some specific security processing to a server. But clearly the combination of hardware and the async there gets you to levels of security processing that the straight CPU is unable to reach. The demo that we have there mirrors this picture where we're using, I think, 22 cores, each talking to 200 clients. and looking to get to 36,000 sessions per second to establish a secured layer and then tearing it down. All right, again, QuickAssist is a marketing term, but again, it's supported by products, and we'll look at even some of the vendors and how to get that product. But it's also a technology that's found in, existing purpose-built hardware there. So you could see a couple of the large OEM players there with public acknowledgement of the use of our technology to offer best-in-class performance in their products. So how do we get to some of this QuickAssist hardware? And I've provided links. So again, the session will produce a PDF where the URLs will be usable there. And so we've provided here a few choices on getting some of this hardware. You have both Intel provided PCI add-on module as well as third parties. And again, depending on your need there, both on the capacity as well as PCIe connectivity, you have multiple choices when you're looking at adding additional security. So hardware is the start, but again, it needs to be complemented with software to make it usable. And as I've said, the OpenSSL work is jointly being done with the OpenSSL Foundation. So this is a key value or key premise that Intel, when we do software enabling, we want to make sure that that's scalable and usable by the entire community, as well as other CPU architectures will benefit some of the advancement of these frameworks. During the process of working through the solutions, though, we certainly always make available early patches or experimental patches to any of those users that are willing to take on what's early on and integrate into their overall solution. And this is the pointers that I'm making available through our public website. So this QuickAssist technology at this point, it's not a confidential, it's not a per design win type activity. This is generally available technology with drivers for current generations available through our open source distribution point at 01.org. You'll find both the QuickAssist driver, the OpenSSL library patch, and then the NGINX patch if you're willing and able to undertake the slight modifications to NGINX to get the most out of an async implementation. And then, of course, we complement that with instructions and then a support mechanism for you to ask questions as you're going through that process. All right, so that's what's usable today. And I think for a lot of us, well, let me see by a show of hands, how many have actually worked with a deployment where you've used PCIe add-on modules to augment security? One hand, maybe a couple others, yeah. So some are working on it, and once you, well, again, that's the purpose of me being over here, is to show you that you have options. We continue to augment our CPU's capability, and you'll see some of the latest numbers using our continued enhancements to AES and GCM. But then if your particular deployment has to do more on the server, you have additional options. All right, but what about future collaborations? So now we've dealt with some of the compute-intensive algorithms like public key exchange. What about even an unsecured environment where you're handling lots of sessions through one NGINX, load balancing applications, and now you're running into the limitation of what's possible through a standard Linux kernel stack? This is where some of our investment in what we call the data plane development kit. So this is a set of software, but it's also a set of concepts and guidance on how to get the most out of packet processing, or how do you get the most I/O through a general purpose processors. It started out as a Intel specific investment, but again, we saw the broad applicability both to Intel architecture, but other architectures. This is really how to do the most I/O on a general purpose processor. And so this has been quite successful for us to help with, even within the proprietary build boxes, on moving from ASICs, network processors, to a flexible software, modern type of design on a general purpose processor. Well, there's the opportunity here. How do we get to take advantage of some of the learnings and benefits to then apply to help with an NGINX type approach when it continues to push more and more sessions in a load balancing type deployment? This is more appropriate, so we've had this slide as just to bring home the point. I just made the comment that you could do a lot of packet processing on a general purpose processor. Clearly, this is a simplistic case. This is a packet coming in. The hardware delivers it into cache. We have very good performance. We have excellent cores for doing lots of instructions there while keeping it in cache. So this is a 5-tuple layer 3 forwarding type algorithm. And you can see these kinds of numbers of 300 millions per second are more typical numbers achievable in an ASIC or in a purpose build. But it brings home the point that when you pay attention to how you're processing the I/O, you could do quite a bit on general purpose processor. Well, in an NGINX deployment, you don't have the luxury of redesigning your application and a custom network stack to get to the bare metal, let me get the most out of a processor. You're dealing with the standard Linux frameworks, the standard Linux TCP IP stack. And that will turn out to be a bottleneck. If you look at where you could push some of these deployments, you're now running into the limitation of the kernel needing to do buffer copies and task switches to the user space applications. So this is where we have lots of experience with DPDK and some of its learnings to say, hey, if I could get the kernel overhead minimized, and I give that CPU cycles to the application, I'm going to move this into new performance capability that was not previously possible. And that's what the exploration that we're working on with NGINX is, how do we bring the DPDK library, how do we work with one of these open source TCP IP stacks to take advantage of the CPU cycles and apply it to getting the I/O right to the user space application. We kicked this off about a month ago, working with NGINX, providing some guidance to Intel on what are the configurations, how do we set up a baseline activity on doing a comparison with the path straight through the Linux kernel stack versus using a DPDK approach, and we have some positive early measurements, and we believe that this is a fruitful activity that the two organizations are going to pursue. But it's not just Intel and NGINX. As you can see, these are open source projects that see the value of getting to the next level of performance measurements. So this is something that we're going to be releasing back into these open source TCP IP stacks, and you would expect to see in future NGINX releases to take advantage of this. Another software ingredient that we acquired, so again, this is specific to workloads. This one is regular expression, and so NGINX in some of its deployments does more or less regular expression. It depends on your ACLs, it depends on the type of rules that you're looking to establish. But in different parts of, especially a network, if you're looking at deep packet inspection, specifically, you're going to find that, again, you're doing compute-intensive algorithms, and we went ahead and acquired an optimal implementation in software. And again, with Intel's preference to scale, this software will also be available in the public domain. So this is a decision that was made very recently. And I think this may be the first public forum where we're actually showing that commitment to making it available for download in a public forum by the end of the year. This has roots in a small company out of Australia. Again, Australia seems to be a hotbed for a lot of the technology aspect. But Sensory Networks started its life as building hardware, purpose-built, regular expression, and soon learned, as we have found, that with Moore's Law, we could get you a lot more compute cycles every year and a half, every 2 years. And so their hardware solution couldn't keep up with the pace of the CPU innovation. And so they converted all of their engineering effort from a hardware aspect to a software aspect. We're early on in seeing which of NGINX type of deployments would actually spend a lot of compute cycles on regular expression. So right now, NGINX links up with PCRE. This is like an order of magnitude better performance than PCRE. But if you're not doing much, if you're only consuming a couple of CPU cycles, it doesn't matter that you have an order of magnitude. So we're looking to jointly get to guidance on their specific deployment use cases that we could provide the end user and say, hey, by the way, there's another software component that for this type of use case will get you benefit. And again, these are ideal type numbers. So with our own, controlled environment, but just showing you that what if you were dedicating the entire CPU to regular expression and that data was available there in memory, you're talking about, you're talking about reaching, 200 gigabits per second or more. So again, not real life, since an application has to do a lot more than regular expression, but it shows what the underlying CPU compute capability is capable of. All right, so we've gone through that quickly, but I hope that I exposed a couple areas that really not necessarily eye-opening, but goes to show, hey, what else could you do with the best-in-class CPUs? And we talked about, available technology now for security, the Intel QuickAssist, and how to acquire that, how to integrate that in. We've talked about our tight collaboration with the OpenSSL Foundation, in addition to NGINX, for getting the async type of architecture support within the application. And then lastly, I showed 2 areas of collaboration that we're right in the middle of right now, and one is how do we get a better TCP IP stack, or I wouldn't say necessarily better, but how do we get the network stack not to be the bottleneck and unleash the application for doing its job. And then also the exploration into where a good regular expression library helps in the deployments of NGINX. I'll open it up for questions now. Yes? Oh, okay.
Is there a microphone?
No, I don't see one here.
Is there a microphone?
So I'll repeat that question. So the question was, whenever you add hardware, you're going to end up potentially maxing out that hardware capability. Like I showed over here, I showed that you reach the hardware capability in 8 cores. And I got a lot more cores there available. So the question was, is there the opportunity to, when you're hitting the hardware limitation, to then pick up in software? I think this is a good opportunity. At least some of the thinking that we had is along the lines of directing it to one or the other. So our OpenSSL engine, for example, is smart enough to know if you're doing AES GCM and you're sitting on top of this type of platform, hey, don't take the overhead of going to the hardware. We weren't thinking about looking at the overall system and saying, hey, what about the resource capacity? I mean, we're dealing with thinking about integration with OpenStack, where OpenStack is aware that there's hardware acceleration on a particular node and could select those applications that need the extra security. But you raise a good one that we'll bring back, which is think about also the resource utilization, dynamic resource utilization. Yeah, so the comment was he's seen this before where it's either one or the other, but ideally you want to use all your resources available on the platform. Very good comment. Yes?
You mentioned the OpenStack now, and of course NGINX. Are there other projects that you guys have been collaborating with closely to take advantage of the QuickAssist API?
So I think those are the two primary ones. We have the OpenSSL async work has been one of the major R&D development. The other one is in the general category of enhanced platform awareness for OpenStack. But then there's a bigger one about making sure this is readily available in all your OS distributions. And it's got the driver support as well as, you're talking about user space access over here and optimized user space access for performance. We're about to undertake, so in a public forum, and a lot of you may not be aware, but in the telecom transition, the network function virtualization, they're looking at how to use servers for doing traditional infrastructure type workloads. They're in a public forum of the data plane acceleration subtask force, things like virtualize VirtIO to these specific devices so that you could get full live migration, you could get full support across platforms. So that's early on. But right now, from a usability aspect, it's OpenSSL, OpenStack, and making sure you got your distributions in line. Any other questions?
On one of the earlier slides, you'd shown comparing just vanilla OpenSSL to a hardware implementation, and I think it scaled to the right across cores. Can you just talk about the software that was used to benchmark it? What was the server? What was the load? And just how that was all set up? Yeah. That
paragraph there in small font, right? Yeah. So essentially, I don't have the technical breadth, but think about that. We have one server simulating clients, and in the demo out there, each client, I think it's 200 clients get directed to a core, and what you're doing is you're kicking off the TLS handshake, and then you end up transmitting like a 0-byte content, and then you're tearing it down. So that's what I understand about the workload. Now, from an environment aspect, we've captured which NGINX version this was, which specific OpenSSL, and that's our patched OpenSSL, and then what the hardware configuration is. So this is our latest Haswell configuration. And you can see that you max out on using only 8 of our lots more cores there for hitting this hardware limit.
I guess my comment was just even looking at just the software implementation, some of those numbers seem pretty high just compared to what you get on commodity hardware. So I was wondering if you're doing something specifically special.
Well, this is what Intel's good at. That's Moore's law. So actually, that is released OpenSSL library, and that what you're seeing on the bottom row there is if you are buying the latest generation servers, and you're using this exact configuration for a TLS handshake, you're going to get a lot more sessions per second than you did on prior generation, and we're committed to continuing to improve that on the CPU.
Is this on localhost, or are the connections generated from outside the machine?
So the bottom row is doing the processing all on the local cores.
Not the processing, the source for the workload. So you have a benchmark. Where is the workload for this benchmark?
On a separate server.
Separate server. Yeah. And what is that separate server running, to generate those connections?
That one I'm not sure. We've documented what the target environment is, but the one that's simulating the 40,000 client sessions, I'm not sure. I think we just made sure we had a server that was powerful enough to drive that. Is that what you're asking about?
Yeah, what's running on the other side and actually making sure that actual connections are being made and done correctly?
Yeah, we could provide those details. I didn't think about it. It's another one. I wouldn't be surprised if this is another one of our latest platforms that happens to be around the lab. Do we know, MJ, on what this is in? We have the demo running in our DuPont lab, and we're remotely connected here. It's 2 machines. I wouldn't be surprised if they're both Haswell type class servers, right? Yeah.
And what software is running on the other side?
That we have documented here. So both the Linux and the NGINX and the OpenSSL version.
That's all for the server. What's on the client side?
Yeah, that's good input. We haven't had that request before to document the client side, but I see your points, like how do we know you're really setting that up properly? Now that's something we could document also. Looks like there's still, yes.
I have a question about, so far you all talk about using Intel hardware support to improve the third-party module performance. So how about NGINX, the performance of NGINX itself? So I ask this question because I saw a lot of code don't care much about branch misprediction. And I actually measured the performance before, and I see the branch misprediction is pretty bad. So
I missed that. I could only hear part of it. So I think I'm hearing, what about the NGINX performance itself?
Yeah, so I asked this question because I once measured the performance before, and I tried to get a cycle breakdown, and I see the branch misprediction is pretty bad. So I just wondering how ICC can improve the NGINX performance, and any other technique can improve NGINX itself.
Okay, so the question was, are we working to the level of really looking at where the system is spending its CPU cycles, and then look where you refer to ICC, which is Intel compiler tools, see where that could help. I think we have an opportunity now with the 2 organizations working closely, where Intel brings that strength to understand what's going on the system and how to help. The proof point is the one that we're doing. Right now we're trying to get to an order magnitude better, not squeezing 5–10% yet, but we're nowhere near that. We're trying to bypass the Linux kernel and give the I/O right to the bottom of NGINX. So that's that user space. That will then, once you get that going, that'll give us the opportunity to look at really what else is going on. Where is the next bottleneck? So all I could commit to you is that there is R&D investment both at Intel and NGINX that want to see the continued performance improvement on IA. Any other questions? Well, thank you for spending time with us, and I'm available if there's other questions.